Hello, I'm going to give you a brief recap of what we've done so far and an introduction to DeMorgans theorem. Firstly, we looked at an AND gate. Looks like this. And the Boolean expression, assuming that the inputs are A and B, is this: A with a blob B. We also looked at an OR gate, way back at the start. It's got a curve back on it. And the symbol for that, when we're writing it as a Boolean expression, is a plus, A or B. And we also looked at a NOT gate, or an inverter. It's only got one input, always. Triangle, circle on the end, and the Boolean expression for that, assuming that what's going in here is A with a bar above it. That's what we get out. So we put in A, we get not A out. We then went on to look at the last two gates, NAND and NOR. And these are just and OR with an inverter on the end. So we draw an AND gate, put a little circle to represent the inverter. We don't draw the whole triangle. A and B. And the Boolean expression for that, there's the AND gate, there's the inverter at the end of the whole lot. Similarly for NOR, looks like an OR gate, gets a little circle at the end for an inverter, and then we say A or B, but the line over the top makes it A NOR B. What I want to show you now is how we can use a single type of gate to do all 5 functions. So let's look at a NAND gate, and we'll say that the only thing we have in our little electronics box of bits is lots of NAND gates. Well, if all we have is NAND gates, it's not hard to make a NAND gate because we already have them. So the first one is taken care of. There's just a NAND gate. Easy enough. But what if we wanted to have an inverter and all we had was NAND gates? So if we want to have an inverter but we don't have any inverters, all we have is NAND gates, and what we can do is take our NAND gate, 2 input NAND gate, and we just join the 2 inputs together. That will act as an inverter. You can do the truth table out and check it out, and you'll see that that becomes an inverter. So now our NAND gate can be a NAND gate, or it can be an inverter just by joining the 2 inputs. But remember, a NAND gate already is AND with an inverter in the end, and if you invert something twice, you're back to where you started. So we can actually also make an AND function using these. We just go into the NAND gate, and then on the output, because there's already an inverter here, we add a second inverter, and we make that inverter from another NAND gate. There we go. We've now got the AND function. If we go in here with A and B, out here at the output we've A and B. So one gate, NAND, doing 3 jobs. In actual fact, it can do all 5 jobs, because if we want an OR gate, all we have to do is put an inverter at each of the 2 inputs. So we get our NAND gate, join the inputs together, set it here, We get another NAND gate, join the inputs together. And we feed those two into a normally configured NAND gate. That will do the OR function. If we go in here, A, B, at the other side we'll have OR. We'll get a 1 if A is a 1 or B is a 1. So now we've done 4 different functions using our NAND gate. And as you might suspect, we can also do NOR, because NOR is just OR with an inverter on the end. So if I go and grab this not very well drawn circuit, and I then add to the end of it another inverter in the form of a NAND gate with the inputs joined, there is the NOR function. So we've built all 5 functions using NAND gates, which means that we only ever need to use NAND gates, and we can build every logic function there is. And the same applies to NOR gates. You can use just NOR gates to make all of the functions. So I'm going to show you how you can make any Boolean expression just using one type of gate. But in order to do that, we need to play a game. For the meantime, we'll just call it Joe's game. And in Joe's game, there are only 2 possible moves. The first move you can make in this game is you can add 2 lines above a letter or a group of letters, because that won't change anything. A bar or a line above it is an inverter. If you add 2, you're back to where you started. So if you've got A, that's the same thing as A with 2 inverters on it, because it inverts once and then it inverts back to where it was. If you've got A and B, then that's the same thing as A and B with 2 lines above it. Now you may be thinking, well, what's the point? You're going to see the point shortly. If you've got A or B, then there's no problem you applying the first move and converting that to A or B with 2 lines above it. It's no longer here spoken as A or B, but we'll leave that for the moment. Let's say we have an expression like this. I haven't bothered putting the Q equals here, but don't worry about that. Let's say we have A and B or A and C. Well, there's no problem with putting 2 lines just above that side if it suits our purposes. Or you could just put 2 lines just above that side, or you could put 2 lines above both sides if you wished. Remember, we're playing a game here. You're going to see why you would do this shortly. And you could also actually put 2 lines over the whole lot. So we could end up with, we don't have 2 lines there, but we drop 2 lines over the whole thing. All of those are, that's a legitimate move. Adding 2 lines above the bracket, that's a legitimate move. Adding 2 lines above the whole thing. What if we had something as simple as A and B or C? Well, this should have a bracket around it like this. So if we want to add 2 lines to this, We can either come along and add 2 lines just there, or we could add 2 lines above that, or we could add 2 lines above the whole thing. The only thing that we cannot do with regard to adding our 2 lines is this. We can't have 2 lines there because that's half in a bracket and half out. Okay, so that's a no. So that is the first move that we're allowed to do in our game. And there only are 2 moves in this game. Let's look at the second. So the second move in this game is that we can also break a line, where we can break it at the point above the symbol if we also change the sign. So we can break a line if we change the sign. Remember earlier we had a NAND gate, A NAND B. There's the symbol for it, A NAND B. And what we can do with that is, I'm just going to copy it across. We can break this line as long as we also change the sign. So those two are the same. And if you think back to the earlier part of this video, we figured that out anyway. That's one of the equivalences I put up. We can use NAND gate to create this function. So we can break a line as long as we also change the sign. If at the start we had this function, then we could come along and break the line and change the sign. But we would only be breaking one of the 2 lines, the one above the sign. So in this case, we would break the line and we would change this sign. So the equations either side of the arrow here do the same job. Move 2 is legitimate move. Move 1 was we can add 2 lines. Move 2 is we can break a line as long as we change the sign. So it's by playing this game, which only has 2 moves, that we can convert one function into another. So let's say we have an AND function. We know we write that as A and B. But let's assume we only have NOR gates and we need to build that. Well, we figure it out by playing this game with the Boolean expression. We take our A and B. I'll just make a copy. And, well, I can't apply the rule that says break a line and change a sign because there aren't any lines, but I can apply the other rule and I can add 2 lines. That is a legitimate move. So the move from there to there is within the rules. I'm now going to copy this one. This is why Microsoft Paint is so handy when you're actually doing this, because the ability to just copy and rub out. And now I'm going to apply the second rule. I'm going to break the line and change the sign. And that is also a legitimate move, the move from there to there. So what am I left with now? What does this thing look like? Well, this looks like We've still got our two inputs, of course, A and B. Except now we have not A. I'm going to just recolor these. So we've got not A. So this is going to be a NOT gate, but we're only using NOR gates, aren't we? So we'll have to use a NOR gate to make our NOT gate from. So we've got a NOR gate there. I'll take a different color for the other one. We've got an inverter there as well. Again, we'll have to use NOR gates to make the inverter. And then finally, we have a NOR gate here, because there's the plus symbol and there's the line over the top. So we have another NOR gate sitting here. So there is our circuit. We started wanting to do the AND function. We wrote it down in Boolean. We played our game and we came up with this. And when we draw it, we have that. And this will do the AND function even though it's built from NOR gates. Let's look at an even more complex example. So here we have A NAND B and A and not C. So that circuit looks like this. Here's the A NAND B, and then we've got an OR gate here, and A and not C. So if we wanted to build that using only NAND gates, we're going to take this expression and start applying the two moves to it in whichever way we think is going to work. Well, I can see a NAND gate here already, so I don't think we're going to have to do much with that. But this is just AND, so this is going to need some work. So the first thing I would do is put two lines here. That makes the dot and the bottom line here a NAND gate. Next thing I would do is put two lines over the whole thing in order to address this plus symbol here, this OR symbol, so that I'm going to break this bottom line and change that sign. Once I break the bottom line, then having broken it, I end up with three short lines on this side, two short lines on this side, and one line across the top, and I've changed the sign. There's no point having three here. We can cancel a pair of those. Can't cancel one line in the same way you can't add one line, but you can cancel two in the same way that you can add two. And once I cancel those, I'm left with this. And that circuit looks like that. So this circuit will do the same job as this circuit. Now it does have an extra gate in it, but they're all the same sort of gate. So this is a much better way of building the circuit. And it's also the case, it's not always the case that you'll end up with more gates. Sometimes you end up with fewer. So the last thing that needs said here is that this isn't called Joe's game. Okay, it's called DeMorgans theorem. I can't claim credit for figuring out how this works. So practice using DeMorgans theorem, using the two rules, the two moves in the game, and then you can apply that to your assignment.